So now we want to use our knowledge of calculus to learn how to find the volumes of irregular solids. And up to this point in your mathematics experience, you have learned how to find volumes of prisms, pyramids, cones, cylinders, those types of things. And all of that has been based on the assumption that if you have a prism, for example, I have a square prism right here, my base is my square, I could simply take the area of the base and multiply it by the height to get the volume. And that's all based on the idea that no matter where you chop your prism, so if I have a horizontal line and I cut it vertically this way, every cross section I get is the same as the shape I had at the front, at the base. So if you just simply take the area of the base and multiply it by the number of layers, the height, you're going to get the volume. So the pentagonal prism here, same thing. I have a pentagon at the front, at the back, and if I chop somewhere in the middle, again I got an identical pentagon. So I can simply take the area of the base times the height. And that's my general process for prisms and cylinders. Here's a cylinder, same idea. If I take cross sections perpendicular horizontally, the way this is laid, my cross sections are the same circle all along. So to get the volume, all I need to do is take the area of one of those and multiply it by its height. Now when we move on to cones, we have more of a problem, because if we chop perpendicular to a horizontal line, our cross sections are circles, but they're changing in size. So it's not the same circle throughout. So the question is, how do you find the volume of that? Well, through our experimentation and discussion, we were able to learn that if you have a cone and a cylinder with the same base and the same height, then the volume of a cone is a third the volume of the cylinder. And similarly for pyramids versus prisms. Now when we come to the question of a sphere, and if I think of this in terms of slicing, this becomes more problematic even more, because if you slice, think of taking an orange or a basketball, your cross sections when you cut are going to be circles that are changing throughout. So how do you calculate the volume of a figure like that? And here's a more extreme example. Take a look at this figure. Now this looks rather irregular. It's not a prism, it's not a pyramid. It just seems to be a solid of some type. You can see a cardboard model of it down here just in terms of what it looks like. How would I find the volume of something like that? Well, if we look a little bit closer, if we think of this as the x-axis, and if we think of our slicing idea, so a big razor blade coming down this way, let me just show you what one cross section would look like. So here's a cross section. Turns out that every cross section, no matter where I move it, is a square. Now we're going to think of this as an infinitely thin square, and they all, these cross sections change depending on where we're at. But if we were to take the volume of each of these cross sections, we would get the volume of the solid. Alright, there's a visualization of the solid with 4 or 5 cross sections. You'll notice that the width of them is fairly large, but if I increase the number of them, and if I think of taking the volume of all of those collectively, they're all changing as we move from left to right. But if we were able to sum up the volume of all of those individual cross sections, we would get the volume of the solid. So that's how we're going to handle shapes that are irregular, is we're going to think of cross sections. To get the volume of an individual cross section, we're going to take the cross-sectional area of it and multiply by its thickness. This will give us the volume of an individual cross section. And then if I want to find the volume of all cross sections, I can take the sum of that, and we know that the sum of this can be expressed as a definite integral. So you'll have your definite integral from the starting point to the ending point of your cross-sectional area multiplied by your thickness. And that will allow us to find the volume of irregular shapes, assuming that they have a consistent shape in terms of cross-section. The cross-sectional size may change, but if it's a consistent shape as we move from one end to the other, then we'll be able to find the volume through this process. Let me just show you one more solid and how we can use cross-sections to find its volume. We have a wedge here, something like that. You can kind of get a sense of what it looks like. And if I look at my x-axis and I chop perpendicular to that this way, let's look at an individual cross-section. In this case, it turns out to be an isosceles right triangle. This distance and this distance are equal, and this leg is at 90 degrees to this one. And as I move from left to right, all of my cross-sections are isosceles right triangles. They change in size, but the shape remains the same. So all I need to do is find the volume of one cross-section, which is the area of the triangle, times its thickness, which is infinitely thin. Take an infinite number of them, add them up, and I will get the volume of my solid. Alright, let's look at a couple of examples. Find the volume of a solid whose base region is a circle with radius 1 and whose cross-sections taken perpendicular to the x-axis are squares. Alright, so I'm going to just draw this out. And because I'm drawing in 3D, I'm just going to make my x-axis go like that, y-axis go like so. I've got a circle with radius 1. And our cross-sections are taken perpendicular to the x-axis. So if I do my chopping this way, now what I want my cross-sections to be are squares. So if I take an individual cross-section here and I extend it upwards the same amount, so this is going to be like the side length of my square. If I extend it upwards, a cross-section would look like so, with thickness. This is precisely the example I showed you just a few moments ago. Right here, where you've got your circle. As you move from left to right, you've got different cross-sections. Your side length is this value, and you're extending it upwards. And if you take an infinite number of cross-sections, move them to infinity, you're going to get the volume of the figure. So in this question, we need to come up with the cross-sectional area times dx, which is your thickness of an individual cross-section, and we're going to sum these up between our starting point, -1 and 1. Alright, so how do we get our area? Well, this distance right here is the f of x value doubled. So at a given value of x, your height, this distance in blue, is f of x, and since we're going below it the same distance, it's going to be 2f of x. So we need to isolate our equation for y, which would be y is the square root of 1 minus x squared if I just want the top piece. This will be 2y. 2 square root of 1 minus x squared. That's our side length. We're going to square it. dx. Alright, we can do a little bit of simplification here. This would be 4, 1 minus x squared dx. Okay, we'll just pop that expression into the calculator, and we're coming up with 5.3 repeating, which is 16/3. Okay, another example. Find the volume whose base region is the region bounded by these two curves, y equals x squared. So the region bounded is like so. And we want to take cross-sections perpendicular to the x-axis. Here's our individual slices. And we want an individual cross-section to be a square. Cross-sections can be whatever we want. They're going to make it a different solid depending on what they are, but this time we want them to be squares. So we want to take a cross-section, extend it upwards the same distance, so there's an individual cross-section. So we want the area of that times infinite thickness, which is a piece of x, in order to give us the volume of that cross-section. Then we'll sum them up. So to get this distance here, that would be the the top function's y value minus the bottom function's y value. In other words, this will be x minus x squared. And therefore the area of the cross section will be that squared. And therefore the volume of the solid will be the cross-sectional area times thickness to get the cross-sectional volume. Sum up all the cross-sections between the starting point, x equals 0, and the ending point, which is the point of intersection there, 1. And we punch that in the calculator, we get a small value as a fraction that is 1/30. Alright, now I'm going to take the same region and I'm going to create cross-sections whose cross-sectional area is a semicircle. So how would that change what I just did? So I have my cross-sections as always. So here's an individual cross-section, and what I want to do now is take that and create a semicircle going like so, with a very small thickness. So since this is a half circle, I'm going to need pi r squared divided by 2 to get the area of that. Now this distance again, remember right here, would be x minus x squared. So in terms of cross-sectional area, my area is going to be half of pi radius squared. This is the diameter we said. So the radius will be that divided by 2. That's our cross-sectional area times thickness to get the cross-sectional volume, and then we need to sum up all such cross-sections between the starting and the ending point, and that gives me my volume. So just to simplify this expression, if I square out the top and square out the bottom, this is going to become 4. If I combine that with this, that'll be pi over 8 pulled out front, x minus x squared squared dx. This was the same calculation we did in the previous question, and that came out to be 1/30. So to get our new volume, it's going to be pi over 8 multiplied by that, so it's going to be pi over 240. Throughout this video, I've used a number of applets and websites to try to show you visually what's going on with volume, and understanding what's going on visually is really half the battle in understanding volume. So I've listed some of the sites here that I've used, as well as others that are very good. I encourage you to check them out to get a better grasp as to what's going on. Now just before I end this video, I want to talk about one particular type of volume by slicing, which is called volume by revolution. So this is kind of a subset of what I've just talked about, a special case of what I've just talked about. One way of creating solids is to take a region of the plane. So for example, here's a square root function bounded by x equals 0 and x equals a. Region is in blue. And I'm going to create a solid from this by revolving that region around the x-axis. Okay, so if I come down here, I can get a bit of an animation as to what that looks like. I'm going to take that region and it's going to revolve around the x-axis, and as it does, it's going to sweep out, or it's going to create a solid. You can imagine what that's going to look like. It's kind of going to be like a parabolic reflector, something like that. Now if I do my slicing again perpendicular to the axis of revolution, I'll notice that here's one particular cross section showing up, which is what we call a disk. It's a circle with an infinite thickness, and as I move from left to right, the disk changes. But if we sum up the volume of all those individually thin disks, we will get the volume of this entire solid. And you can find the volume of that by taking the area of the circle, which you know is pi radius squared, multiplied by its thickness, and then sum up from the beginning to the end. Alright, so not all solids are created through revolution, only solids whose cross sections are circles, as you can imagine, will be created through revolution.